Hi everyone. So for the project, I found a colorectal cancer registry dataset. The dataset was published by a government agency, Public Health England. So it contains about 600,000 observations of patients with known colorectal cancer diagnosis in England from the years 2000 to 2017. So the dataset contained mostly categorical variables such as age group, sex, diagnosis year, tumor site, cancer stage, tumor morphology, underlying cause of death, tumor grade, vital status, and basis of diagnosis. So the only numerical variable in the data is this one. So the days between diagnosis and vital status date. So basically, number of days starting from the patient being diagnosed with cancer to the day of death. And for the project, I decided to use cause of death as the target variable. So classifying the cause of death being from CRC related, so colorectal cancer related, or no CRC, so dying of other causes or other diseases. So admittedly, building models to predict the outcome or cause of death of a colorectal cancer patient is not the most ideal. It doesn't really address a primary business problem, but it does hold potential future implications that I will discuss at the end of the presentation. In the beginning, I was hoping to find a data set that would have features that can be used to build models to predict, instead of the cause of death of a cancer patient, to maybe being able to predict what the likelihood of a person developing colorectal cancer. But it was just very difficult to find an open source clinical data set. It's probably due to like HIPAA laws and privacy protection laws. So I decided to just go ahead with this data set and try to make the most out of it. So as you guys know, before any modeling can be done, we just have to do some data exploration first. So instead of using the entire 600,000 observation data set, I decided to do like a subset of the data for these reasons. So I decided to just look at data from 2012 and onwards, just because tumor staging wasn't really, well, cancer staging wasn't really available prior to that in the data. And I believe that cancer staging is probably a big predictor for the cause of death. And I removed the vital status, so either deceased or alive. And then I also removed the column tumor ID just because it just wasn't useful. And the second part that I explored was just the distribution of the predictor variables. So I looked at the overall split of the target variable first, and then did some visualizations of the main predictor variables. I also tried to see if there are any outliers in the one continuous feature, and tried to do summary statistics and built a histogram to just visualize the feature. And I'm thinking for the models the algorithms I'll be using, there is concern with collinearity. So since this is mostly categorical variables, I did multiple chi-square tests to test for independence between the predictor variables. And in the end, selected and omitted some of the features just based on the p-values obtained from the chi-square test. So for pre-processing of the data and shaping the data, since it's mostly categorical variables, I did some data cleaning, so like reducing the number of factor levels when possible. And for that one continuous variable, I did have to convert some of the blank rows to NAs after looking at how the column was defined from the source data. And since it is a continuous variable, I had to do some missing value imputation. So using the mice package, which is very neat, and I will show you how the code works in a bit. And besides imputing, I also had to do some binning for that variable, so just using the cut interval function to do that. And once that was all done, I split the data set into training and testing sets. I decided on an 80% training, 20% testing set. So overall, the clean data set had about 75,000 observations, which is, a pretty decent size. I apologize. So I'm having problems screen recording my R notebook. So I will just show you the HTML file downloaded from the R notebook. So speaking of imputation, so I said that I use the mice package. It's a pretty neat package. So basically you take a variable, a feature variable out of your data set, and you set some parameters. So right here you can see the call is just M for you can choose the number of imputations that you want to do, the number of iterations to impute the missing values, and the method. And since it's for numerical data, you have to put in predictive mean matching as the method. So for my data, I use 100 iterations, and at the end, you'll see it runs pretty quickly. It does 100 iterations of imputation, and at the end, it just spits out an imputed version of your data set. And after imputing the NAs, I also had to bin the variable, so the days from diagnosis to death variable, using the cut interval function from tidyverse. Since I didn't really know where to cut or set the bins, I decided to just use 4 bins, and it managed to be 4 bins. So the bin 1 is just number of days equals 1 to 627. Bin 2, 627 to 1,250, and so on. And after the data subset has been cleaned and processed and split into training and testing sets, I chose 3 algorithms to build models out of, I guess. So the first algorithm chosen was the naive Bayes algorithm. So I chose it because it's relatively simple and fast. It's well suited for categorical data. It can handle binned numerical features. It performs relatively well even when the assumption of independence of the features do not hold true. And I tried my best to eliminate features that are dependent of each other but using the naive Bayes algorithm, it shouldn't be an issue. The second algorithm chosen was the decision tree. So I chose it because one of the advantages is that it's able to handle large data sets. Again, it's appropriate for categorical features. It doesn't require extensive data preprocessing. It can handle the outliers and the missing values. It's easy to interpret. And then the third algorithm, random forest, it's similar to decision tree, and the advantages are pretty much the same. It's more accurate typically compared to just a single decision tree, but also it's harder to interpret compared to the decision tree. So after using the training set to train the algorithms and tested the models by creating cross tables to evaluate accuracy, I ended up with a few iterations of the models. So I built a naive Bayes, like just from the default settings, a naive Bayes model. The second one being a naive Bayes with the Laplace smoothing estimator put in. I set it as Laplace equals 1. I created a decision tree from like default settings, tried to boost the model. I also tried to apply like a error or penalty cost to the decision tree. So the logic behind that is that I set a penalty for every time the model made any mistakes of predicting a cause of death as CRC. As no CRC when it was actually death caused by CRC. So, and as for the random forest model, I use first like the default settings again, and then from that I fine-tuned it by just adjusting the hyperparameters. And again, this is just a little run through of my codes. So for the naive Bayes model, I used the E1071 package. So this is just building the model, making prediction using the testing set, and setting up a cross table to evaluate the accuracy. And then, so just a few iterations of the naive Bayes model. And for the decision trees, I use the C50 package. And like I said, first just trying a model using the default settings. And calculating the accuracy rate again. And just making different iterations of the models. First by boosting, and then by, like I said, setting penalty values. As for the random forest, I use the random forest package first with default parameters. So the default parameters set number of trees created as 500, and had the number of variables sampled at each split at 2. So I tried to fine-tune, made some adjustments to the parameters for the second iteration of the model. So this time just changing the number of trees in the forest to 300 instead of 500, but still keeping the number of variables sampled at 2. So in the end, this is just a quick summary of overall accuracy rates of the different iterations of the models. As you can see, they're very close. They're very similar, with just the random forest model just slightly better than the others. For my ensemble model, I built that by incorporating the three best iterations of the naive Bayes and the decision trees and random forest models built. So the ensemble was done by using bootstrap aggregating or bagging method, specifically just using like majority voting methods. So since there are only three models in the ensemble, we didn't have to worry about them being a tie in the end. So I basically reshuffled the original data set to the train and test sets to use for modeling the ensemble model. And from that, again, just calculating the accuracy rates. And at the end, the ensemble didn't do much better compared to the individual models, the accuracy rate being around 70.2% at the end. So to summarize, we built models using the naive Bayes, decision tree, and random forest algorithms. I really wasn't able to improve on the accuracy rate of the models even after making adjustment and trying to boost the models. So some key lessons learned from the project is that the target variables, being cause of death, wasn't really the best or most interesting to make predictions out of, but it does give valuable insight as to like future potential data sets that we can use similar predictive models on. So in this context, for example, like I said in the beginning, it'll be helpful to have a data set that captures colorectal cancer risk factors and factors used to diagnose cancer, such as like medical history, patient family history, the frequency of access that patients go to do their preventative screening for colorectal cancer, so colonoscopies. And then the tumor staging if they have cancer, and the rate of recurrence of the cancer. And then using these features, I think there's a good chance that we can use similar algorithms to make predictive models to predict the person's likelihood of developing cancer, or how likely their cancer will recur based on the diagnosis. So yeah, that is it. Thank you so much for your time.